Hello and welcome to lecture 52. We are discussing about transonic compressors. So in last lecture we were discussing about different kinds of aerofoil which are being used for transonic compressors. Name say maybe double circular arc aerofoil, controlled diffusion aerofoil, multiple circular arc aerofoil, S type of aerofoil. Now in last lecture we were discussing about how the flow, that's what will be behaving when we are using such kind of aerofoils. So what we have observed, say when we are discussing about double circular arc aerofoil, it says this is what is a kind of aerofoil what we are using when we are having flow, that's what is in the range of nearly Mach number of 1.4 or less than that. Under that condition, when it will be striking on the blade, because of say rounded leading edge, we will be having bow shock, that's what will be formed. So the use of rounded aerofoil, that's what we have realized now. We are not interested in making sharp edge aerofoils. Let it be multiple circular arc aerofoil, let it be S type of aerofoil. We will be having our leading edge and trailing edge to be slightly rounded. Okay. Now for double circular arc aerofoil, what we have observed, because of the curvature of my suction surface, downside of my shock, so we will be having two shock kind of formation. First, that's what is initially been striking on the blade, and second shock, that's what will be forming within the flow passage, we can say is a passage shock. So because of curvature of our suction surface, we will be having expansion fans which will be formed. And when my flow, that's what will be reaching to passage shock or near to the location of passage shock, we will be having Mach number nearly same as what it was at the entry of my flow, means entry Mach number. And from there, because of presence of this normal shock, we will be having downside flow to be subsonic flow. So here in this case we will be having supersonic expansion, that's what we can say equivalent to supersonic diffusion, and subsonic diffusion, that's what is happening. So during 70s, 80s, this is what was working fine, and that's what was mostly being used. Even as on today, for many fans and compressors, people they are using double circular arc aerofoil. Then we have seen, in order to have systematic management of the flow in sense of formation of shock on the blade surface, using computational tool, this diffusion control aerofoil they have been developed. So here in this case we will be having whole lot of acceleration, that's what will be happening on the suction surface in the range of Mach number nearly 1.3, and then after we will be having smooth diffusion, that's what will be happening on the later part, and my Mach number or my flow, that's what will be remaining nearly constant on my pressure surface, and this is what was giving very good flow behavior as per the expectation. And these blades we have discussed, they are white chord aerofoils and they are having say some special applications. Now moving to the next, we were discussing about the multiple circular arc aerofoil. The difference here is, rather having two circular arc, we will be having four circular arcs, and maximum thickness location, that's what is in our control. We can move forward towards the leading edge or maybe towards the trailing edge, and that's what will be helping us in sense of managing the flow on the suction surface of the blade. And that's what we have seen here, because since this is what is, say we are having the suction surface shape such a way that rather having the expansion fans, we will be having say shock fans, that's what will be forming on the surface, and that's what was giving supersonic diffusion, and that's what was followed by subsonic diffusion. So when we are having Mach number above 1.4, rather using double circular arc, we are going with multiple circular arc. even going crazy if we are having say inlet Mach number in the range of 1.8 or 2, we can go with this kind of aerofoil, that's what is say S-type aerofoil. If we compare this, we can say when our blades are highly staggered, under that condition this kind of aerofoil straightway can be used. Most of the diffusion in S-type aerofoil, that's what is happening because of supersonic diffusion, and only small portion that's what is responsible for the subsonic diffusion. So we can say we are able to achieve very high pressure rise by using such kind of aerofoils. Now in the case of double circular arc, we can say it's a jump diffusion kind of configuration. Here we are having systematically management of my shock, and that's what is giving systematic distribution of my diffusion. Now with this, let's move ahead in sense of understanding what exactly is happening when we are using that for the testing purpose, or when we are having this compressor that's what is working. So if you recall, this is what is representing the performance map of single stage transonic compressor, where this point N, that's what is representing my design condition. So like this is what is a maximum peak efficiency condition. Point A, that's what is representing nearly stall condition. Point B, that's what is representing choke condition, and we can say point C, that's what is having say lower back pressure configuration. So this is what is been reported by Block and O'Brien. So here in this case, if we try to look at what is happening in sense of shock formation within the blade passage, let's see, suppose say we are considering peak efficiency point. So here in this case, we are having, this is what we can say the passage shock, that's what will be forming. Somewhere here we will be having normal shock, and that's what was giving say considerably high pressure rise, that's what we are expecting, and we are having peak efficiency. The peak efficiency is because we are having minimization of the loss, that's what is happening. Now here in this case, if we move towards point A, we will be having this oblique shock, that's what will be striking here, and that's what will be giving say nearly stall condition. Here it is interesting to observe, if we look at carefully this particular region, since this is what is my normal shock, downside I will be having sudden change of pressure, and that's what will be giving adverse pressure gradient. So there may be chances of my flow to get separated. So by changing small mass flow rate, it may possible that my aerofoil will go stall. Okay. Now in the case of point B, we can see this shock, that's what is moving downside towards the trailing edge. So here somewhere we will be having the flow, that's what is getting choke under this kind of mass flow configuration. Small change of my mass flow rate or change of back pressure, it may be possible that the shock will be standing exactly at the trailing edge, and there is no further increase of mass flow rate, that's what is possible. So we can say like not only we need to focus when we are discussing for the development of such aerofoil for design condition, we also need to think what flow phenomena, that's what is happening when we are going under stall condition or when we are going for choke condition, because that's what is limiting our performance and operating range. Now in order to understand say how exactly my shock front that will be standing, so because of ability of flow visualization techniques PIV, some of the experiments and their results they are being reported here. So these are say low hub casing ratio rotor. So this is what is being tilted at say 20-degree interval in order to realize the shock front. So here you can say this is what is under near stall condition. We can say above around say 40% of my span we will be having shock front, that's what will be forming. This is what is exact location when we are tilting at 20 degree. Now what happens when we are having say peak efficiency configuration, under that condition, as we have discussed earlier also in last slide, say what happens, we will be having the movement of the shock towards the trailing edge. So we can see here, this is what is representing the movement of our shock towards the trailing edge. Now if we look at carefully under this, what exactly is happening? So suppose say this is what we have discussed, say this is what is nearly stall condition. What happens, we will be having our normal shock that will be standing here. In later part we will be having say flow separation or say presence of low momentum fluid downside. Now this what is happening, if we look at for say overall blade, say this is what is my transonic compressor blade. So this is what is a location where we will be having passage shock, and this what we say in sense of formation of separation, that's what will be going say strong outward flow in the boundary layer, that's what will be moving towards the upside. So this is what is representing the movement of my flow on upward side. So this is what will be creating trouble near my tip region. We can realize we are having the differential pressure on pressure surface and suction surface, that's what will be giving my tip leakage flow. Along with that we are having shock flow, and that's what will be creating whole lot of trouble to the flow in the tip region. Okay. Now let's try to look at what all we have learned in sense of our subsonic aerofoil and supersonic aerofoil. Let's try to understand how my flow parameters, that's what will be affecting my flow behavior within the blade passage. So here if you recall, this is what is representing my Mach number distribution on the cascade, subsonic cascade. Subsonic cascade we can say it's a C4 aerofoil or maybe DC aerofoil or say NACA 65 aerofoil. What is happening? We are having the acceleration of flow, that's what will be happening from 5 to 10%, where we will be having maximum acceleration, and thereafter we will be having the deceleration of flow, that's what is happening on the suction surface. And we can say on pressure surface we will be having the acceleration of flow, and later on it will subjected to say flow deceleration. And this area under this curve, that's what is representing my pressurizing capacity of this particular aerofoil. Now suppose if we consider we are having say transonic aerofoil, say here this work it has been reported by Cambridge University, Professor Miller. What they have done, they have taken say transonic aerofoil which is been having say inlet Mach number of 0.9, the inlet flow angle is 53 degree, say flow turning angle is 14, and area ratio we will discuss very soon, throat area to inlet area is 1.05, and say pitch to chord ratio is 0.9. Now when this aerofoil is subjected to different inflow conditions, suppose if you consider say varying the Mach number 0.6, 0.8, 0.9, 0.95. So here if you look at, since this is what is aerofoil, that's what is a transonic aerofoil, and our inflow condition is a subsonic kind of configuration, we can say this is what is representing what is happening on my blade suction surface and pressure surface when my Mach number is 0.6. When I am increasing my inflow Mach number, we can see we will be having say acceleration of flow, that's what will be happening on my suction surface, nearly up to say 40% of my span. And thereafter this is what is represent the formation of shock, and later on we will be having the deceleration of the flow, that's what is happening on my suction surface. Same way we can say this is what is happening with our say pressure surface, we will be having the acceleration of flow, and in later part we will be having the deceleration of flow, that's what is happening on my pressure surface. So the meaning is, what we are looking for at this moment is, suppose if we are having our aerofoil to be transonic aerofoil, and if it is subjected to say subsonic inflow condition and say maybe design condition, how my flow that will be behaving. Okay. Now in order to realize that part, let's see, this is what is a very interesting plot that's what is representing what is the effect of change of incidence angle. So this is what is representing when we are having say our inflow condition or inflow Mach number to be 0.6, and this is what is when we are having inflow Mach number to be 0.9. Now in order to distribute the losses, say Professor Miller, they have divided the losses in different categories. They have divided in sense of non-boundary layer kind of losses, suction surface losses, pressure surface losses. Now in case of non-boundary layer kind of losses, it says like downstream mixing losses. We can say what is happening towards the trailing edge, that's what we can say as downstream mixing losses. We are having shock losses, we are having attach loss, shock induced separation, trailing edge diffusion driven separation. On pressure surface we will be having attach loss and leading edge separation loss. So let's try to realize what is happening when we are having our inlet Mach number to be 0.6. Now here in this case, if we look at, this is what is a particular region when we are having our incidence angle, that is what is positive. Do not forget, when we say our incidence angle is positive, means my flow that will be striking towards the pressure surface. Now if that's what is your case, what is happening here? If you look at carefully, in this particular region near our suction surface, we will be having flow acceleration, that's what will be happening. So here in this case we will be having shock formation, that's what will be happening. Okay. Now since this is what is been formed, we can say this is what is say location 4, that's what is called say shock induced separation. Because we are having this separation, that's what will be forming because of this acceleration, what it will be doing, it will be moving towards the downside. So in this particular region we will be having the flow separation, that's what will be happening. Okay. Now because of this flow separation in downside direction, we will be having our mixing loss, that's what will be going to be increased. We will be having thicker wake, that's what will be coming out. So we can say in this region we are having say trailing edge diffusion driven separation, and we are having say downstream mixing losses, that's what is going to boost up. So we can say this is what is representing my mixing losses, this is what is representing my diffusion driven say separation, and this is what is say shock induced separation, that's what is happening. So we can say when our flow is subsonic and our incidence angle, that's what is say positive, this is what will be giving rise to the losses. Now towards say negative incidence side, suppose if we look at say my angle to be -6 degree, what happens? So here in this case when we say it's a negative incidence angle, my flow that's what will be striking towards my suction surface, and that's what will lead to give my leading edge separation. So here we will be having leading edge separation. You can say with increase of incidence, this leading edge separation losses, that's what is going to be increased. Okay. Now this is what is representing when we are having our aerofoil to be transonic and it is subjected to subsonic flow or subsonic inflow condition. Suppose if I consider say for the same aerofoil my inflow Mach number is say 0.9. Suppose if we look at say we are having 0 incidence case. So even for 0 incidence case we are having the presence of shock losses. You can see here what is happening when we are having 0 incidence, I will be having whole lot of acceleration, that's what will be happening on my blade surface, and that's what will be subjected to have say shock losses. So here we are having shock losses, that's what will be forming. If we are moving slightly downside, maybe if we are changing this say incidence angle say 0.58, under that condition we will be having suction surface separation, that's what will be happening in this particular region. Okay. When we are moving towards the downside, suppose say Mach number in the range of say incidence angle in the range of say maybe 3.3, under that condition we will be getting some different kind of flow physics. Okay. Here in this case we will be having shock induced separation, that is what will be very large. We will be having say downstream mixing losses also will be very large, and we will be having shock losses. So, we can say my losses, that is what is going to increase when we are having our incidence angle in the range of maybe 3.2 or 3.3. Now, towards the negative incidence direction, if we are going here say maybe around maybe incidence angle of minus 2.2 or 2.4, under that condition if we try to look at, we are having, this is what we can say is say my shock losses. So, shock losses we can see, this is what is my blue color one, and because of I am having negative incidence, we will be having the formation of shock here, that is what will lead to give say leading edge separation, and that is what is increasing my losses. So, when we are comparing these two for low subsonic Mach number or say subsonic Mach number of 0.6 and Mach number of 0.9, we can say our operating range, it is very sensitive. Just look at the numbers. So, here we can say we are having the losses to be rising for say incidence angle of 6. Here in this case when we are talking about the transonic aerofoil, this incidence angle which will lead to give more losses, that will be in the range of maybe 3.2 to 3.5. Okay. So, we need to be very careful, that is the reason why we are saying when we are using our subsonic aerofoils for supersonic flow or supersonic aerofoil for subsonic flow, we need to be very careful, we need to catch an eye for all kind of loss formation, that is what is happening. Okay. Now, let us try to move and try to understand what exactly is happening within the blade passage. So, here if you look at, these are the two aerofoils, they are being arranged in a stream tube configuration. Here if you look at, this is what is representing my acceleration of the flow on suction surface, that is what will be having say end with the normal shock here. So, this is what is representing for the variation of pressure for this particular streamline. We can say in pitchwise direction we are selecting one of the streamline. So, this is what is one of my streamline. If we are putting or we are tracing what is happening with the pressure, you can see this is what is representing the variation of pressure. Now, in the case when we are having say presence of this blade, we can say we will be having the deceleration of the flow, that is what is happening, that is what will lead to have say rise of pressure ahead of our leading edge. Now, since we are having the acceleration of the flow, that is what is happening on say suction surface, that is what will lead to reduce my pressure. So, this is what is representing reduction in the pressure. Somewhere here we are having normal shock, and this is what has been representing sudden rise of pressure. We can say this is what is sudden rise of pressure, and later on this particular region, that is what is subjected to, we can say when we are having subsonic diffusion. So, this is what is representing my subsonic diffusion. Now, this dotted line what we have taken, that is what is when we are considering our flow to be completely subsonic, and when we are considering our flow to be completely supersonic. Say this is what is with say subsonic entry of 0.9. So, when we are considering low subsonic configuration and when we are considering supersonic range maybe Mach 1.2, 1.3, this is what is representing. Okay. And somewhere here we will be having the interaction of this say subsonic solution, and this is what is for this particular location, that is what will give the location for the throat. So, this is what is representing the location of my throat. We can say throat definition, that is what is same here, that is where we are having minimum area. Now, let us move ahead with the same kind of configuration, rather having one streamline, let us take three different streamlines. Say here this is what is say near to my suction surface, this is what is nearly at the mid station, and this is what is towards my pressure surface of other blade. So, here in this case if we try to look at, this is what is representing what is happening with my pressure distribution. So, now for green, for red line and for this blue line, this is what is happening. Now, if we try to look at here, since this is what is more towards the acceleration region, and that is the reason why we are having more acceleration, that is what is happening here. Comparatively less acceleration, that is what will be happening here for the second streamline. And here if you look at, this is what is not coming in say acceleration region, and that is the reason why this is what is not subjected to any kind of shock formation. So, this is what is say continuous kind of flow in sense of diffusion, that is what is happening. For all the three lines, if we look at carefully, this particular region where we are having throat to be placed. So, we can say our throat, that is what is at the common location. Now, this is what is representing what is happening when we are having our design configuration and zero incidence case. Let us try to look at what is happening with the change of area ratio. So, what we mean by area ratio is, here in this case we can say somewhere here we are putting this as my inlet area. This is what is representing my minimum area, we can say is a throat area, and this is what is the exit area. So, for this aerofoil, design area or design area ratio is 1.05. So, this is what is representing what is happening with our isentropic Mach number. So, if we look at carefully, if we are changing our throat area, the location of my shock, that is what is changing, and we are having different configuration of the acceleration, that is what is happening on the suction surface. So, if we try to look at here, suppose if we consider say three different area ratio, and if we are putting together say for the area ratio of 1.05, this is what is representing in sense of what is happening with the normal shock, and we can say this is what is representing the strength of my shock. Okay. When I am increasing my throat area, this rise of pressure, that is what is going to be large, and that is what is showing like the strength of my shock, that is what is going to increase. And our location, that is what is say my throat location, that is what is coming at the same place, but their location or say the placement, that is what is somewhat different. So, we can realize how we are managing our flow by changing the area ratio. So, this is also one of the possibility. Do not get confused when we say we are changing area ratio in order to manage the flow, maybe small change in sense of thickness or maybe change of say location of maximum thickness, that is what will be helping, or maybe we are changing the movement of our curve camber line, that is what will be helping in order to achieve the change of this throat area. Now, next case that is what will be coming is in sense of change of say pitch to chord ratio. We must realize here, we can say this is what is in line to what we are discussing in sense of say number of blades. So, change of this pitch ratio, that is also having considerable effect on say the flow configuration. So, here in this case if we look at say these are say different pitch to chord ratios. Say design pitch to chord ratio is 0.9 and we have reduced to 0.7 and say maybe 1.1. If you look at the peak Mach number, that is what will remain same, only the location of my normal shock, that is what will be going to change. So, here in this case if we are comparing, so it says like when we are having say different pitch to chord ratio, we will be having the location, that is what is going to change. Okay. And this is what is changing the strength of my shock, and that is what will be lead to change my flow parameter or flow behavior in the later stages. So, this study, that is what is very important for our study. Now we can say, like, what all we are discussing is, we have started discussing about the airfoils, especially transonic airfoils. Then after we were discussing about the formation of shock. Then we were discussing about how my flow, that's what will be behaving on my suction surface and on my pressure surface. Later on, by understanding of that, we need to do systematic management of our shock, and that's the reason why we are looking for special kind of blade surfaces. We are looking for special kind of camber lines. We are looking for arrangement of pitch to chord ratio. We are looking for what is happening with the change of incidence angle. We are looking for how the area ratio, that's what will be affecting my flow behavior. Now, looking to all this, that's what is giving indication to us, saying like, how to develop all these blades, how to design these blades, how to get the coordinates for pressure surface, how to get the coordinates for suction surface, what need to be the leading edge radius, what need to be the trailing edge radius, what need to be my camber line, what need to be my maximum thickness. So all these things, that's what need to be known to us. Suppose if we know, we will be having initial simulations using the computational tool. Based on, say, received result or what all results we are getting, do post processing. Using that post processing, try to understand how my flow is behaving in the blade passage, and as per the requirement you can modify the shape of your blade, and that's what is people they are doing. So in next lecture we will be discussing about how to develop different kind of camber lines, how to decide the thickness distribution, how do we arrange our blade as per our requirement. Thank you very much for your kind attention.